Physics is an ever-prominent aspect to the natural world. Its effects and contributions are witnessed in ways people don't realize exist, like the loudness of the radio and the specific patterns in sports like softball. However, one of the most underrated pieces of human existence that is constantly intertwined with physics is cars.
The creation of a car undergoes immense scientific thought and consideration in order to minimize the risk of injury in collisions and increase someone's safety potential. When manufacturers build their cars, they contemplate what safety features may be best in relation to the laws of physics and the natural world. To begin with an obvious criteria of physics presence, we have Newton's 3 laws, which apply to every aspect of car accidents. These laws describe the motion of a body in response to the forces acted upon it. The first law of motion pertains to inertia, stating that an object in motion will remain in motion until another force acts upon it. In car wrecks, this becomes the case with one primary example, seatbelts or inertia inhibitors, because the person inside the car traveling the same velocity as the car wants to move in the same direction the car was going if the car immediately stops. However, seatbelts prevent this. Newton's second law also plays a role. In this law, the direction of the force vector is the same as the direction of the acceleration vector. Newton's third law plays its part too, which led directly to the creation of airbags, because for every action, which might be a car accident, there's an equal and opposite reaction, and the airbags work to absorb a body's opposite reaction to a sudden stop in a car. Can be defined as mass in motion. All objects have mass, so if an object is moving, then it has momentum. It has mass in motion. Momentum depends upon the variables mass and velocity. The momentum of an object is equal to the mass of the object times the velocity of the object. If an object has a large momentum, it either has its mass or its velocity is large. A fast-moving car has more momentum than a slow-moving car, assuming they have the same mass. A heavy truck would have more momentum than a small car, assuming they have the same speed. So the more momentum an object has, the harder it is to stop, and the greater effect it will have if it is brought to rest by impact or collision. The law of conservation of momentum states that in an isolated system, the momentum before a collision is equal to the momentum after a collision if we disregard friction. If cars of unequal mass collide, the more massive car will force the smaller vehicle backwards, and the smaller car will experience more force. We can see that momentum lost by the larger car was gained by the smaller car. In car collisions, there are 2 types of accidents, elastic and inelastic. Collisions in which objects rebound with the same speed, having the same momentum and kinetic energy as they had prior to the collision, are known as elastic collisions. Elastic collisions are characterized by a large velocity change, a large momentum change, a large impulse, and a large force. An inelastic collision is a collision in which the kinetic energy of the system of objects is not conserved. In an inelastic collision, the kinetic energy of the colliding objects is transformed into other non-mechanical forms of energy such as heat energy and sound energy. Any collisions in which the 2 colliding objects stick together are said to be inelastic collisions. Impulse is measured as the product of force and time in which that force acts on an object. In a collision, the change in momentum cannot be changed, therefore the impulse cannot be changed, as according to the impulse-momentum equation. However, the ideas of impulse can be used to reduce the force upon impact. Most driver's education classes teach future drivers that the stopping distance of a skidding car is directly proportional to the square of the speed of the car, based off the work-energy theorem. That means if a car is traveling at 10 miles per hour, it may require 4 feet to skid to an abrupt halt, but a car going twice as fast, 20 miles an hour, would require 4 times the distance, 16 feet, to skid to a stop. A doubling of the speed results in a quadrupling of the stopping distance. The stopping distance is directly proportional to the square of the speed of the vehicle.
Created using Powtoon.